Assalamu alaikum warahmatullahi wabarakatuh. Welcome to the third experiment of EE235 Electronics and Microcontroller Lab. This is Ahmed Fawzi and I will be explaining the pre-lab for you today, inshallah. We are going to explore three concepts in this lab. First, superposition. Second, Thevenin and Norton theorem. Third, the maximum power. So let's start with the first concept, which is superposition. The superposition theorem states that in a linear circuit with several independent sources is the sum of the currents and voltage produced by each source acting independently. The theorem is valid for any linear circuit. For a linear circuit containing multiple independent sources, the current or voltage at any point in the circuit may be calculated as the algebraic sum of the individual contribution of each source acting alone. The idea is to isolate the effect of two or more independent sources. For example, if we have an electric circuit with three independent sources, so we are going to isolate the second and third independent sources and calculate the voltage that are coming from the first one. After that, we are going to cancel the first and third one and calculate the voltage that is resulting from the second source. After that, we are going to isolate the first and second and check the voltage that is resulting from the third independent sources. After that, we are going to get the algebraic sum of these voltage. For example, V total will be equal to V1 plus V2 plus V3. Noting that V1 is a voltage that is resulting from the first independent source. V2 is a voltage that we have got from the second independent source, and V3 is a voltage that is coming from the third independent source. Superposition theorem works only for the circuits that are reducible to series parallel combination for each of the power sources at any time. It only works where the underlying equations are linear, no mathematical powers or root. For example, as we have explored in last experiment, we have discussed Ohm's law and we have reached to the linear relationship between voltage and current. Superposition applies for voltage and current, but it is not applicable for calculating powers or something which has roots. So the requisite of linearity means that superposition theorem is applicable for determined voltage and current. So a question might come to your brain: can superposition work for power calculation? So the answer is no. Power dissipations, being nonlinear function, do not algebraically add to an accurate total when only one source is considered at a time. Steps to apply superposition principle. First, turn off all independent sources except only one source. So if you have voltage source, you need to make it short circuit. For current source, you are going to make it open circuit. Second step, find the output voltage or current due to the active source using the circuit analysis techniques. Third step, repeat steps 1 and 2 for each of the other independent sources. Fourth step, find the total contribution by adding algebraically all the contributions due to the independent sources. Consider the voltage signs and current directions while adding. Let's have an example to illustrate what we have discussed in superposition theorem. For example 1, use the superposition theorem to find V in this circuit. Solution. Since there are two sources, let V equal V1 plus V2. V1 is due to source 6 voltage and V2 will be due to 3 ampere source. So first step, let's isolate 3 ampere current source. So when we are going to isolate current source, we are going to make it open circuit. So we will remove it, cut it from the circuit, and the circuit will be reduced to the following. We have right now one independent source which is 6 volt, and we are going to calculate V1 over the 4 ohm resistor. V1 from voltage divider rule, it is 6 volt multiplied by 4 ohm over 8 multiplied by 4, which will give us 2 volt. After that, we are going to return 3 ampere independent source back and remove 6 volt. But when we remove 6 volt independent source, we are going to make it short circuit. For independent sources, current sources, we are going to make it open circuit. For voltage source, we are going to make it short circuit. So we are going to bring a wire here. And we have returned back 3 ampere. So right now we are going to calculate V2 over the 4 ohm resistor. In order to get V2, we need to calculate I3 first. I3 will be calculated through using current divider rule. I3 will equal to 3 ampere multiplied by 8 ohm over 8 ohm plus 4. After that, we are going to calculate V2 by multiplying I3 with 4 ohm, which will give us 8 voltage. After that, we are going to apply the algebraic sum V total equal V1 plus V2. V1 is 2 volt, V2 is 8 volt, so the resultant is 10 volt. Example 2. We are going to use superposition to find the value of the current I, which is here. Right now we have 3 independent sources, 30 milliampere, 15 volt, and 15 milliampere. So I total will be I1 plus I2 plus I3, which are the currents due to 30 milliamperes, 15 milliamperes, and 15 volt. First, we are going to use 30 milliampere and isolate the 2 other independent sources. As we have here voltage source, we are going to make it short circuit. For the current source, we are going to make it open circuit. So the circuit will become like this. We have removed 15 milliampere, make it open circuit. We are making 15 voltage as a closed circuit. Right now we are going to reduce the circuit. We have here 12 kilo ohm with 6 kilo ohm are connected in parallel. So our equivalent of these 2 resistors becomes 4 kilo ohm. After that we have here 2 resistors. After that, we are going to calculate IA. IA equal to 30 milliampere multiplied by 2 kilo ohm over 4 plus 2, because these 4 and this 4 are connected in series. So IA will become 6 milliampere. From IA, we are going back to the above circuit. IA is here. It is known right now. We are going to calculate I1 from IA. I1 equal to IA multiplied by 6 over 12 plus 6, which will give us 2 milliampere. Right now we are going to calculate the current due to 15 milliampere acting alone. So we are going to make 30 milliampere here as open circuit and 15 voltage as closed circuit. The circuit will become as follows. We could transform 15 milliampere current source to a voltage source. To make it voltage source, we are going to use Ohm's law, V equal IR. We have here I, we have here R. 15 multiplied by 4 equals 60 volt. So it is now replaced with a voltage source. Right now we could get IB. To get IB, we are going to use Ohm's law. We have here 60 volt over R. Our equivalent is calculated as 12 kilo ohm is connected in parallel to 6 ohm. After that, we have 4 kilo ohm is connected in series with 2 kilo ohm, and they are together connected to the equivalent resistance of these 2 parallel resistors, 12 and 6. So IB will be 60 over 2 plus 4 plus 6 in parallel to 12 will give us 6 milliampere. From IB, we are going to calculate I2. I2 from current divider rule will be 6, which is IB, multiplied by 6 kilo ohm over 12 plus 6, which will give us 2 milliampere. Third, we are interested now in the third independent source, which is 15 voltage. So we are going to isolate 15 milliampere by making it open circuit and 30 milliampere by making it open circuit. The circuit is reduced to this circuit. Right now we are going to calculate IC. IC from Ohm's law equal to the voltage source over R equivalent. R equivalent, we have here 2 plus 4 and here 12 with 16 are connected in parallel. So IC will be minus 1.5 milliampere. And here do not forget the sign. After that, we are going to calculate I3 from IC by using current divider rule. So I3 equals to IC multiplied by 6 over 12 plus 6, which will give us minus 0.5 milliampere. Right now, we are applying the algebraic sum of superposition. I equal to I1 plus I2 plus I3, which will give us 3.5 milliampere. For the first part of the next experiment, you are going to make the circuit in simulation and also experimentally. Please note that we have here two independent voltage source, V1 which is 10 volt and V2 which is 5 volt. So first you are going to remove 5 volt by making it short circuit and calculate the voltage due to V1. After that you are going to remove V1 by making it closed circuit and calculate the voltage that is resulting from V2. The second part of this experiment is Thevenin and Norton theorems, one of the most surprising concepts that arise from linear circuits theory is the equivalent circuit. No matter how complex the circuit, from the viewpoint of any pair of terminals, the circuit behaves as if it is considered only as consists only of a source and an impedance. The equivalent circuit concept simplifies calculation in circuit theory. The equivalent circuit means that a simpler but functionality equivalent form for complicated systems might exist. So to illustrate what we have read in the last slide, if we have original circuit like this, we could simplify it by an equivalent circuit which is simple. They are equivalent to each other. So as you have seen here, the result of the original circuit and the equivalent circuit on the oscilloscope are the same. So we could reduce this complicated circuit to a simplified circuit. How to make that? This is what Thevenin and Norton theorem is about. Thevenin theorem states that a linear two-terminal circuit can be replaced by any equivalent circuit consisting of a voltage source V Thevenin in series with a resistor R Thevenin. Norton theorem states that a linear two-terminal circuit can be replaced by an equivalent circuit consisting of a current source IN, I Norton, in parallel with a resistor Rn. So in the Thevenin theorem, there is voltage source V Thevenin in series with R Thevenin, and we have here R load. For Norton theorem, we have here IN, which is a current source, in parallel to Rn, and we have here a V terminals. After determining Thevenin and Norton equivalent, you could divide V Thevenin by I Norton. It will give you R Thevenin. V Thevenin is the open circuit voltage at the terminal, and I Norton is the short circuit current through the terminal. In order to find R Thevenin, you are first going to calculate the open circuit voltage V open circuit, VOC, across terminals A and B. After that, you are going to calculate the short circuit current I short circuit at terminals A and B. So V Thevenin equal V open circuit and I Norton equal I short circuit. R Thevenin equal to V Thevenin over I Norton. Methods for calculating R Thevenin. First, turn off all independent sources. If you have voltage source, make it short circuit, and if you have current source, make it open circuit. R Thevenin is the input resistance of the network located between terminal A and B. To simplify these concepts, we are going to get an example. It will help you to understand the concept of Thevenin and Norton. For example, find the Thevenin equivalent circuit of the shown circuit between A and B. As we have agreed, we are going to remove the voltage source by making it short circuit. So the circuit will be reduced to this. After that, we are going to reduce the circuit. We have 6 ohm is parallel to 3 ohm. The circuit becomes as this. After that, we have here 10 ohm is series with 2 ohm, so it becomes a 12. Equivalent resistor here is 12 is parallel with this resistor 12. So R Thevenin equal to 10 plus 2 and parallel to 12 ohm, it becomes 6 ohm. Find V Thevenin using mesh analysis. We have here I1, I2, mesh 1, 12 multiplied by I1, plus 10 multiplied by I1, plus 6 multiplied by I1 minus I2 equal to 0. So I2 becomes 14 over 3 multiplied by I1. In mesh 2, we have here minus 18 volt plus 6 multiplied by I2 minus I1 plus 3 multiplied by I2 equal to 0. Reducing the equation, we will have minus 6I1 plus 9I2 equal 18. So from these two equations, we have I1 equal half ampere and I2 equal 7 over 3 ampere. Now we are going to make KVL at this loop. Minus V Thevenin plus 10 ohm multiplied by I1 plus 3 ohm multiplied by I2 equal to 0. So V Thevenin equal to 12 volt. So this complicated circuit will be reduced to a voltage source which has 12 volt and R Thevenin connected in series with it, which is 6 ohm. The good news for you, in the lab you are not going to solve the problem analytically. You are going to make it experimentally, but here we are explaining the concept and you are going to apply this concept on the hardware or the simulation. The third part of our experiment, which is maximum power transfer theorem. The general problem of power transfer can be discussed in terms of efficiency and effectiveness. So we are interested in knowing the maximum power in the circuit in order to have good efficiency and effectiveness. The maximum power theorem will provide us with the efficiency of the power transfer, the amount of power transferred. Consider a general network has a resistive load RL. The problem is to determine the value of RL that permits maximum power delivery to our load. To solve this problem, we are going to replace the network by a Thevenin equivalent circuit, determine a general expression for power delivered to RL. Finally, we are going to solve this differential equation dB over dRL equal to 0 to find R load at which the power will become maximum. Here are the steps. First, we are going to get the Thevenin equivalent. As we have agreed in the previous example, we are going to reduce the complicated circuit to V Thevenin in series with R Thevenin, and we have here in series with R load. Power is the multiplication of voltage with current, or I square multiplied by R load. To calculate I here, we are going to use current divider rule. I equal V Thevenin multiplied by R Thevenin over R Thevenin plus RL. So we are going to replace I in this equation and put it squared and multiply it with R load. After that, we are going to differentiate with respect to RL. So we have ended up with this equation. We are going to solve this equation by equating it to 0. So we have reached now to R Thevenin equal to R load, which is an interesting finding. So we will get the maximum power transferred to the load when the load resistance equal to the R Thevenin, as we have seen from this. So in order to get maximum power in the circuit, you are going to equate RL with R Thevenin. So if you calculate R Thevenin analytically or experimentally, and it becomes, for example, 10 kilo ohm, and you have R load, which might be a lamp or anything, you have to make RL equal to 10 kilo ohm in order to get the maximum power on the circuit. Please note that from the shown figure, the power is small for small or large value of RL, but the maximum when RL equal to R Thevenin. There is a formula for the maximum power, P equal I square multiplied by RL, and as RL is the same, so it becomes 2RL here. If you simplify the equation and get the power max is V Thevenin square over 4RL. For the second part of this experiment, you are going to apply Thevenin and Norton theorems. Besides the maximum power transfer to this circuit, you are going to implement it and calculate V Thevenin, I Norton, R Thevenin, and the maximum power in this circuit, as you will see inshallah next lab. Please note that power here will be calculated in another form by V square over R. Thanks for your listening, and I hope you will enjoy the next lab inshallah, and thanks also for Dr. Lubna. See you inshallah next lab.